Every web request you make physically travels thousands of miles across oceans and server farms before anything happens. When a user clicks Save in a standard web application, the UI locks up and a loading spinner appears. But in modern tools like Linear or Figma, that exact same action resolves instantly. To understand why that spinner exists, we have to look at the network path. Your client sends an HTTP POST request to a server, which then queries a remote database. The database executes the write operation, confirms it, and sends the response back down the wire. That entire round-trip cycle routinely forces the user to wait up to 800 milliseconds. If the user's connection drops for even a second during that transit, the entire request fails and throws an error. This underlying structure has defined web development for decades, and it is known as the cloud-first model. The entire architecture is built on a single strict rule. The cloud database is the absolute, unquestioned source of truth. In this system, the client's web browser is relegated to being a dumb terminal. It cannot validate interactions or update state until it receives explicit permission from the cloud. This creates three major problems. First is perceived latency. Even if you are on a 5G network or fiber internet, data transmission is constrained by the speed of light. Second is system fragility. If an API gateway stutters or a user steps into an elevator, the application completely breaks. Third is server load. Your backend expends massive CPU resources processing repetitive, trivial read and write requests that could easily be handled on the user's machine. Because of the physical realities of global networks, true zero latency is mathematically impossible under the cloud-first model. Escaping the loading spinner requires completely upending the structure. This brings us to the alternative model powering instantaneous software, local-first architecture. These applications eliminate network wait times entirely, allowing a web app to feel as fast and responsive as a native desktop program. They achieve this through a topological inversion. Instead of treating the cloud as the source of truth, the user's local device is elevated to act as the primary authoritative database. The remote cloud server is subsequently downgraded. It acts merely as a secondary background synchronization hub. By putting the database directly on the client, engineers bypass the physical latency constraints of traditional REST APIs. To see how this works, let's build the local-first triad. We start at the origin point, a user interaction, like clicking Add Task. Immediately, the application writes that data to a local embedded database. With no network trip, this takes 0 milliseconds. This is powered by client-side storage technologies like indexed DB, browser-based SQLite via WebAssembly, or powerful tools like PGLite. Executing the write operation locally entirely decouples the data mutation from network latency. The user interface then reads directly from this local database and updates on the exact same 16-millisecond render frame. This creates a system that is inherently offline native. Because the local database is the primary source of truth, the application performs identically whether you are on a high-speed fiber connection or sitting on an airplane with the Wi-Fi disabled. The second layer of the triad handles the external connection, the background sync engine. This engine runs continuously in the background, specifically monitoring the device's current network connectivity state. If the device is offline, the sync worker gathers local database changes and batches them into discrete Delta updates. This brings us to the third and final layer, the central cloud server. The precise moment the sync engine detects a restored network connection, it asynchronously transmits those batch Delta updates up to the cloud. This triad topology successfully removes the network from the user's critical path, but it introduces a severe distributed systems challenge regarding decentralized state synchronization. Shifting the database to the client creates a glaring issue, managing decentralized state across multiple users. Consider a scenario where two users edit the exact same document at the exact same time while both are completely offline. When both users regain their network connection and transmit their Delta updates simultaneously, those independent edits collide. Traditional relational databases fail in this scenario, generating severe merge conflicts or corrupting the data entirely. You cannot use centralized database locking to fix this because you cannot retroactively lock a table for an edit that already happened offline. Local-first systems solve this collision using conflict-free replicated data types, or CRDTs. A CRDT is a mathematical data structure with one specific guarantee. No matter what order the Delta updates arrive, all clients will eventually converge on the exact same state. It achieves this consensus deterministically without ever needing a central server to lock tables or negotiate the merge. We can see exactly how this works by looking at this TypeScript code for a state-based last write wins register. The CRDT record interface tracks 3 properties: the actual data value, a numerical timestamp, and a unique peer ID string for the specific client. When the merge function runs, it first compares the timestamps. The update with the highest, most recent timestamp automatically wins. But what if both offline edits were generated at the exact same mathematical millisecond? The function relies on a deterministic tiebreaker. It compares the 2 unique peer ID strings and selects the higher value, ensuring a definitive winner. Because every single client and server in the topology executes this exact same deterministic math, sync conflicts mathematically disappear without any network negotiation required. While powerful, local-first architecture is a specialized tool, optimized for specific conditions, not a universal replacement for REST APIs. To evaluate when to use it, let's look at an architectural comparison matrix. The left column highlights optimal targets for local-first, highly interactive applications demanding seamless offline capabilities. This includes productivity suites, project management trackers, collaborative Canvas tools, and mobile apps for field workers. Conversely, there are domains where implementing a local-first approach is dangerous. Certain problem spaces mandate strict global consistency across all users at all times. The right column shows systems requiring traditional client-server architecture, ticket booking systems, high-frequency trading, and credit card processing. But when applied to the correct domains, elevating the client to the primary database provides a level of responsiveness that traditional request-response cycles cannot match. Learning to implement embedded databases and background sync engines allows engineers to build software that remains functional and fast regardless of network quality. Escaping the loading spinner requires evolving past the strict rules of traditional web architecture.